So, we have been going over the details of quantum computing and the various aspects of it, and we have also looked at some of the relevant considerations which are required for its implementation. However, one of the basic issues which has come about is that we have not really looked into some of the foundations or the basic aspects of quantum part of this problem. So, I thought in today's lecture we will go back a little bit in looking into the basics of quantum mechanics and take it from there. So, this particular lecture set would be more on the basics of quantum mechanics and looking at some of the aspects related to the quantum phenomena. So, in terms of basics of quantum mechanics, we have already realized that it is quite distinct and different from the classical mechanics, which we label as the Newton's mechanics or the Newtonian mechanics following the laws of Newton, and Maxwell's equations, which are for electromagnetic theory. So, when we consider Newtonian mechanics and Maxwell's equations, we can explain macroscopic phenomena such as motion of billiard balls or rockets. However, when we are looking at microscopic phenomena such as photon atom scattering and flow of electrons in a semiconductor, or the kinds of discussions we have been having until recently, which is miniaturization of computing to try to do quantum computing and other things, quantum mechanics is the main idea. So, quantum mechanics is a collection of postulates based on a huge number of experimental observations. The difference between classical and quantum mechanics can be understood by examining both the classical point of view as well as the quantum point of view. So, let us see. So, the classical point of view, the Newtonian one, the Isaac Newton's one, is the one where the laws are written in terms of particle trajectories. A particle is considered as an indivisible mass point that has a variety of properties that can be measured, all of which we call observables. The observables specify the state of the particle, position and momentum. And here please note that we are mentioning both position and momentum. So, this is what we call the classical particle, and often it is represented in terms of point objects. Just to make sure things simple, point objects allow drawing of path between different points, and that is why it is easier to mention in terms of classical point objects. And here both the momentum as well as position, so these are like position x1, x4, this is the position, as well as this motion associated would be a velocity, and so both position and momentum can be specified, and this is the classical object point. A system in this concept is a collection of particles which interact among themselves via internal forces and can also interact with the outside world via external forces. So, the forces are of different kinds, one is the internal force and the other one is the external force. The state of a system is a collection of the states of the particles that comprise the system. All properties of a particle can be known to infinite precision. Now, this is the part which is very important in classical mechanics, and we have been used to this principle. So, the conclusions from classical look of how we wanted to state is the trajectory is the state description of Newtonian physics, evolution of the state use the Newton's second law. The principle of causality is the fact that two identical systems with the same initial conditions subject to the same measurement will yield the same result. Now, these are the three important aspects of classical concept which give rise to, or which we are used to in terms of classical mechanics. So, one of the important applications of classical mechanics we know is always in astronomical objects like motion of stars, motion of planets. All of this work quite well, solar system. So, we define them in terms of systems as well as individual objects. So, this is all what we describe in terms of classical. On the other hand, in terms of quantum point of view, quantum particles can act both as particles and waves. So, this is the first very important aspect of quantum mechanics, which is it assumes to start with, or it has built in wave particle duality. Quantum state is a conglomeration of several possible outcomes of measurement of physical properties, and quantum mechanics uses the language of probability theory, and therefore, random chance is one of the important aspects that we have to build in quantum mechanics. Another important point here to understand is that the observer in this case cannot observe a microscopic system without altering some of its properties. Neither one can predict how the state of the system will change in terms of absolute precision. And finally, quantization of energy is another property of this microscopic particle, which is different from classical system, because in terms of classical mechanics, energy can be continuous. So, one of the most important points mentioned in quantum way of looking at things is the inability to be certain in measurements, and that comes from the famous Heisenberg uncertainty principle, which says that one cannot unambiguously specify the values of particles' position and its momentum for a microscopic particle. And this is so different from the classical point of view. So, this gives rise to the fact that there is always some error in measurement. At any point of time, the measurement is being made. So, any measurement which is made will have some error associated with it, either in space or in momentum, and that product is always going to be at best equal to h cross, which we know as h cross is h over 2 pi, which I clarify here. At best it is going to be h cross over 2 or more than that. Position and momentum are therefore considered as incompatible variables, or in other words, these are the ones which cannot be measured with absolute precision simultaneously. The Heisenberg uncertainty principle strikes at the very heart of classical physics, the particle trajectory, because if we cannot ascertain position and momentum simultaneously, the entire picture of trying to draw a particle's motion becomes difficult, because neither the position or the momentum can be certain to absolute precision, and that is the reason this becomes one of the biggest problems for classical physics or classical mechanics, that is the Heisenberg uncertainty principle. So, how do we apprehend this? So, in order to make sure that quantum mechanics can still be applied to macroscopic principle, there is something which is sort of like known as the correspondence principle. The idea being that quantum mechanics, when applied to macroscopic systems, it must reduce to the classical laws, or must reduce to the case which the classical physics predicts. And therefore, the non-classical phenomena such as uncertainty and duality must become undetectable. Niels Bohr codified this requirement into his correspondence principle when he postulated his way of looking at quantum mechanics. Now, Bohr's theory is something which is still considered as the old quantum mechanics. What we will now look at is how things have evolved. Now, for him it was necessary to code this because he wanted the correspondence principle of looking at quantum mechanics or applying quantum mechanics to macroscopic systems. So, that is one way of looking at it, but there are now the ideas have evolved to a way that it need not be coded, it comes automatically the way the mathematics is done. So, in principle we have this situation that when we are in the atoms and molecule range in size 10 to the power minus 10 or in that order, then we are definitely in this quantum mechanics domain. And when we are in macroscopic domains, when we are talking in terms of us, trees, buildings, planets for example, then we are all in this classical mechanics principle, and there are laws to connect them, and there are physical models which can lead us to the predictions that we talk about in both these domains. So, the wave particle duality, which is the other main aspect of quantum mechanics, gives rise to the very different behavior of microscopic particles from that of classical particles. So, in essence, in some experiments we have a situation where the behavior of classical wave is shown by particles. So, the particle resembles the behavior of classical wave, that is, it is not localized in space. In other experiments, the particle behaves like a classical particle localized in space. So, in some sense it is showing a duality between the particle and the wave like picture. Corpuscular theories of light treat light as though it were composed of particles, but cannot explain diffraction and interference. On the other hand, Maxwell's theory of electromagnetic radiation can explain diffraction and interference phenomena, and that was the reason why corpuscular theory was abundant earlier. So, this is from earlier times. In quantum mechanics, we are apprehensive of the fact that both can coexist, and that is the reason why the property of light used to have both wave like in terms of Maxwell's phenomena or particle like as far as the corpuscular theory. So, in terms of wave particle duality, we have specific examples where waves as particles exist. Max Planck work on Blackbody radiation, in which he assumed that the molecules of the cavity walls described using simple oscillator model can only exchange energy in quantized units. So, that was one place where Max Planck introduced the concept when he used to study the Blackbody radiation. So, this is the case when particle nature was used. In 1905, Einstein proposed that energy of an electromagnetic field is not spread out over the entire wavefront, but localized in individual packets or quanta. Each quantum of frequency nu travel through space with speed of light, carrying discrete amounts of energy and momentum which are known as photons, which are used to explain the photoelectric effect, and this was later on confirmed through X-ray experiments of Crompton. So, these are the two cases where, for example, we have waves to be treated as particles, blackbody radiation and photoelectric effect. Similarly, for particles as wave, we have double slit experiments where instead of using a light source, if one uses an electron gun, the electrons are diffracted by slit and then interfere in the region between the diaphragm and the detector to give rise to the same kind of pattern which looks like the case of interfering waves. Okay. So, the principle of diffraction and interference are shown by electrons, and therefore, electron particles behave as wave under these conditions. So, a little bit more on blackbody radiation, because this was one of the first important points which gave rise to the idea of quantum mechanics. This kind of radiation has been known since centuries, since whenever a material is radiated, this kind of radiation has been known for centuries, since when a material is heated, it radiates heat and its color depends on its temperature. So, for example, heating elements of a stove turn from dark red to bright red when the temperature goes from 550 degrees centigrade to 700 degrees centigrade, and it can even further go into orange and yellow and finally white when the temperature goes really hot. So, depending on the temperature, the radiation and its color changes. So, the emissive spectrum, as we call it, as a result of this change, depends on the material heating as well as on the material property. Blackbody is defined as a material that is constantly exchanging heat with its surroundings to remain at a constant temperature. It absorbs and emits radiation. The problem is it can deflect incoming radiations, which makes a theoretical description much more difficult depending on the environment and so on and so forth. However, a blackbody is a perfect absorber, incoming radiations are totally absorbed and none is reflected. So, that is the ideal definition of blackbody. Another example of blackbody can be something like a cavity, which is someone shown here, such that a metal box with a small hole drilled in it, the incoming radiation enters the hole, keep bouncing around inside the box with negligible change of escaping again through the hole. That means it gets absorbed completely. The hole is the perfect absorber. For example, blackbody radiation emission does not depend on the material the box is made of. This is generally universal in nature. So, there are many ways blackbody and blackbody radiations can be designed and can be checked, and it has been there for several. This concept has been around for very long. However, the difficulty this principle faced, and it was labeled as one of the outstanding problems at the beginning of the 20th century, was to describe the blackbody emission spectra. It was difficult because classical physical principles could not quite explain what was going on here. So, when attempts to fit the low and the high wavelength part of this spectrum was tried simultaneously, the theory always failed. The theory worked quite well for the high temperature zone, but it always had a problem when it was trying to fit both low and high wavelength part of the spectrum. That is because, as per classical physics, emission spectrum is a superposition of electromagnetic waves of different frequencies, and the frequencies allowed were the standing waves inside the cavity. Again, the equipartition of energy would give rise to the fact that every standing wave carries kT of energy, Boltzmann constant, and temperature T of the energy. The flaw is in this approach that when the wavelength is approaching 0, the number of standing waves keep on increasing, leading to an energy which goes to infinity, and that is why almost all the laws sort of show the theory in terms of classical physics showed that the energy keeps on increasing as the wavelength goes lower. This came to be known as the ultraviolet catastrophe, and that led to the failure of the classical theories. One of the most celebrated work in this, the work of Rayleigh-Jeans, was considered as state of the art using well tested theories which were very good agreement with many experimental results in many other circumstances, and even in this case wavelength part was well explained. Only when the wavelengths went to lower numbers it failed. Thus there was a need of a new theory. So when Planck looked at this problem, he was also an expert in thermodynamics. He assumed that the radiation of the cavity was emitted and absorbed by some sort of oscillators contained in the walls, and this concept is something which he introduced. He used the Boltzmann statistical methods to arrive at the formula, which is the Plancks Radiation Law. Now Planck made two modifications to the classical theory in coming to this form. The oscillators of electromagnetic origin can only have certain discrete energies determined by E equal to h nu, n h nu, where n is an integer, nu is the frequency, and h is called the Planck's constant, which was given by a number which was very small, 6.6 times 10 to the power minus 34, however with the units of joules second, which meant that the oscillators can absorb or emit energy in discrete multiples of the fundamental quantum of energy given by delta E equals h nu. And that was one of the most important points of the Planck's radiation law, which showed that energy was in packets. So this gave rise to the principle of quantization. Blackbody emission spectrum, explained by introducing quantization of energy transfers, resolved the ultraviolet catastrophe. So that was one of the most important contributions at that time in this field by Max Planck. Even at low wavelengths and at high frequencies, this particular theory worked. At small wavelength, the energy h nu needed to fill up the oscillator states, the probability of the occupied oscillators decreased rapidly, that is faster than the rate found in the Rayleigh-Jeans formula. So no ultraviolet catastrophe happened. So at small lambda, the energy h nu needs to fill up, the oscillator states increase, their probability to be occupied then decreases rapidly, for example faster than the rate in the Rayleigh-Jeans formula, so no ultraviolet catastrophe happens. However, it became very highly disputed. Planck himself looked for a few years find whether h could be made to go to 0, the Planck's constant, without any success. So that was the basic principle behind quantization, where even Planck, who discovered it, had difficulty in apprehending. So as a result of Planck's law, the energy, which is the classical one, continuous, any energy could be there, became discrete. The particle could have only specific quantized energies, and this was in conjunction with the idea that there was some sort of a oscillating vibrating particle inside this entire picture, which was being shown to think in terms of blackbody radiation. After this, Einstein in 1905 found out that the same principle of quantization was necessary when he was studying the photoelectric effect. What he found that his law required that the radiation field be quantized. His observations were that when the light fell on the emitter and photoelectrons were being generated, which showed as a potential in the circuit, there was a threshold frequency until which there were no emitted electrons. However, once the threshold was reached, many emitted electrons came out. So, essentially there was a threshold in terms of the energy which was necessary for the electrons to come out, showing that it had a particle property rather than a continuous property. So, this threshold frequency or the threshold energy gave rise to the idea of quantization again. This led to the other part, which was creating a problem in terms of classical mechanics, to look at an atom. In terms of classical mechanics, an electron in orbit around an atomic nucleus should emit electromagnetic radiation or photons continuously as per Maxwell equation, because it is continuously accelerating in curved part. The resulting loss in energy implies that the electron should spiral into the nucleus in a very short time, that is, an atom cannot exist. So, this was one of the issues which the Bohr model was able to handle, because once this concept of classical nature of radiation being emitted at any energy was possible to be looked at differently, he was able to come up with the first quantized atom picture, and that immediately explained the atomic spectra of the hydrogen atom, the line spectra and all that. So, his theory in 1913 was the one where these energies of this electron around the nucleus was considered as quantized, so that the transition of an electron could only happen at discrete intervals, and so only discrete line spectra, which was always observed, was immediately explainable because of this principle. So, the atomic spectra of the hydrogen atom line spectra became understood from this picture introduced by Bohr, and so that is the first Bohr's theory on, that is the first theory on the hydrogen atom in terms of quantized aspect which was given. So, we will get more into quantum mechanics after this lecture in the next one, because we have just come to the point where the first Bohr's model of quantization and the old quantum mechanics, as we call it, is justified by using the principle of packets or discrete energies, which was obvious from the previous experiments and ideas which were necessary to explain this kind of observations that we are observing. So, both Max Planck and Einstein quantization principle of very small energy packets, which were given based on the Planck's constant, were being utilized to give rise to this principle of quantum mechanics. More on this in the next lecture.